Well, thanks for having me here. I'm excited to be here. I'm a geologist with the survey. I work mostly on Paleozoic bedrock of southeast Minnesota, and that includes Washington County. I know you probably get a variety of speakers, and I'm used to just talking geology, so forgive me if I use too many technical terms. One of the reasons I volunteer to do some of these things is for my own practice and presentation. So anyway, let's get to it. Herb's going to help me advance the slides. So I'll tell you a little bit about the survey first. Anybody, I know Herb's been to the survey. Anybody heard of the Minnesota Geological Survey before? Great. Oh.
You know what?
Is it working?
It's not advancing. Let's see now.
Yep. You want to go?
Yeah, I'm doing it here.
Is that working?
Okay.
All right, so this is our main website. You can find us right here online. We still have an office you can get to and find some paper maps if you like to. Here's our address. In 2014, we've moved. So if you've been to the old survey, we're now on the north side of University Avenue from our old place. So we haven't moved far, but we are in a new spot. You can see here kind of our mission statement on the website. We're a research and service arm of the Newton Horace Winchell School of Earth Sciences. So we're part of the University of Minnesota Earth Science Department, but we are in our own building off campus, located kind of between the Minneapolis and St. Paul campus. And you know, our mission, or mostly what we do, is to investigate the geology of Minnesota and provide basic public information on the geology of the state. And we work through the public, county offices, other state agencies, and so on. All right? So most of our guidance, or how we convey our geologic information these days, is through a program called the County Geologic Atlas. There's a few up here. This started about 30 years ago, the late 80s, where we developed a series of paper maps, usually 5 to 6 plates, 5 to 6 different maps within these envelopes about different aspects of the geology of a particular county. So we're going county by county mapping. And you can see kind of the status of where we're at here. Red is completed county geologic atlases. And that yellow color is underway, so you can kind of get a sense of where we're working these days. And different crosshatch patterns mean several different things. Some of these are remaps, maps that had been made in, say, 1980 or 9 or 1990. But those paper maps have become outdated. The data that's come along in the last 30 years, there's a lot more information. And then the products have changed too. So those are reasons why we may do remaps of a particular county. Counties and planners and agencies, they want digital GIS shapefiles to sort of layer in different map software to make planning and land use decisions. And those aren't a part of some of the older maps. They're just, things to put on your wall. So that's the reason why we are doing some remapping, especially in the metro area, and in some of the really older or first county atlases we've done. And then we like to think of it as one atlas, 2 parts. Part A is the geology, and Part B is a second folder, which is the hydrology or the hydrogeology. Okay, and the DNR division of waters is what produces Part B. So they take our geologic products, kind of our containers or so as we speak, and then they tell us about the groundwater in those particular containers. And that's the status of Part B. They're not quite as many because they need Part A to start working on a Part B. So that's the story there. So again, in a typical atlas, there's a series of 6 plates. We always start with the database plate, what was used in the making of these maps. Then we have a bedrock geology plate. Then we have a superficial geology plate, which is more of the, at the very surface, glacial landforms and so on. And then we have what's called a quaternary stratigraphy plate, or a map of the glacial layers, and then a sand distribution model of those sand deposits brought by the glaciers. And then bedrock topography, depth to bedrock, is another map I'll show you in a little bit here. So if you found our website, everything is available, everything we produce is available as a PDF document on our website for free. So if you're interested in perusing any of that, any of the County Geologic Atlas products, you can just search for a particular county and click on any number of these plates, and a map will pull up on your computer or your iPhone. And then what's also here is all of the supplementary digital GIS files, and we assume that the public isn't the main user of those. It's other counties, agencies, and so on. But everything we produce is online. I'd just like to take a minute too to say a little bit about a Part B. This is as much as I'm going to say about Part B's. Part B's investigate the groundwater hydrogeologic setting, aquifer distribution. They address pollution sensitivity, groundwater recharge, and subsurface flow in the aquifers. They're generally in a thicker report and several plates, and then they also have their GIS files online. And the hope with these Part Bs is that they're used to make land use decisions that take into account aquifer sensitivity, water quality, and sustainability. So here's, if you clicked on Bedrock Geology of Washington County, here's the map that comes up. And I know this is blurry and hard to see, but just to make the point that there's a lot of different pieces on the geologic map. You've got not only the map, you've got information about the different units, a lot of text describing how those units got there in the first place, what their age is, and anything else about the geology. And then there's some cross sections and some additional figures. And I'll talk quite a bit about all those things as we go along here. Another way that we're looking at distributing this information is something called a story map. So if you went on our website, you can find several of the county geologic atlases we've done recently. We've had a GIS specialist put together this information into what's called a story map. And you can click on one of those. If you go to the next slide, this is what it looks like if you clicked on Washington County. And it's just a way for you to click on one of those individual plates and zoom in and zoom out and find where you live and zoom in and see what the different geologic layers are. So a really useful tool for just the average viewer of some of these maps. When you get to the paper copies, it's really hard to sort of zoom in and look at things site specifically. So this is one of the newer tools we've been playing around with to convey our information. So let's get into the geologic story a bit here. I know you hear a variety of speakers, a variety of topics. We're going to talk about history that's really old today. The geologic record of Washington County is not continuous or complete. We have recent glacial deposits at the surface, and those are generally 2 million years old or less, and part of what's called the Quaternary era. And then most of the rock that I study, and we're going to talk about in Washington County today, is Cambrian Ordovician in age and Paleozoic. So, and it's around 450 million years old. Beneath those rocks are the Precambrian hard rock that these rocks were deposited on top of, and I'll talk a little bit about those as we go. And in terms of just material and thickness, glacial deposits are anywhere from hundreds of feet thick. Paleozoic rocks are on the order of thousands of feet thick, or hundreds to thousands of feet thick, and then the Precambrian rocks exist at great depths down to the crust. Okay. So here's where we're sitting today. So you can see the Paleozoic rocks cover much of Wisconsin and southeast Minnesota. Those rocks, again, are Cambrian and Ordovician in age. And you can see they're color-coded out here, Cambrian in yellow, Ordovician deposited on top of that in the light blue, and we have some Devonian-age rocks just in the very southern part of the state. And they exist in sort of these pancake-like layers that were deposited on one another. And the bottom of the stack is primarily more sandstone-rich, or what a geologist would refer to as siliciclastic, just more silica-rich. And The top of the stack is more dominated by carbonate or limestone and dolomite rocks. Okay? And these rocks are deposited much like, you know, the oceanic setting you'd see today on the coast, right? The sandier facies or deposits are deposited closest to the shoreline. The finer grain sediments get carried out a little bit farther and deposited as mud or shale. And then further offshore is where the carbonates or limestones like to form, where there isn't a lot of wave agitation and mud and sediment moving around. So you just kind of think of these in terms of grain size and distribution laterally. And as sea level rises and falls, I think maybe I have a slide about that on the next one. As sea level rises and falls, your position of these rocks and where they're deposited is just reflected of where that shoreline's moving. They march forward as sea level rises, and it marches back out as sea level falls. Okay? And that's important because, well, I guess the record we have today is just that. It's a record of that sea level rise and fall over time. And if you took that cross section, you can see that there is a mix of coarse clastic or coarse sandstone. So if you've heard of the Jordan sandstone, the St. Peter sandstone, or the Mount Simon, those are all coarse grained, nice, beautiful, sandy rocks. The next unit we refer to, or the next major rock type, is just a fine grained sandstone, so a little bit finer grained size, or shale. So that would be in the darker tan colored here, and this would be the coarse sandstone in the lighter yellow. And then the third rock type we refer to is the carbonate, and that's kind of in the green. So you can see the mix of the different units and how they stack. And it's important we recognize those differences in textures, mainly because they have differences in terms of how water moves through them, right? If you poured water on a coarse sandstone, it's going to go into the rock and kind of fall into it. If you poured water on a shale, it's going to fall over it. Some water is going to seep into that, and some is just going to go right along the side. And if you poured water over a limestone, it's just going to go right over the top. And those are just because if you looked at it microscopically or at a finer scale, there's different amounts of pore spaces between those grains, right? And the highest porosity rock is the coarse sandstone. It has the most pore spaces, or most air, or areas for water to be stored than in some of the finer grain units. Okay? And another thing, just thinking about the hydrogeologic picture, rocks generally behave as either an aquifer or an aquitard based on those components. So a sandstone transmits water readily through those large, well-connected pore spaces. Fine-grained sandstone or carbonate rocks generally provide confinement, where due to that poor connectivity in small pore spaces, they don't transmit water well. However, at the aquifer scale, all those matrix components contain fractures and conduits. And that's one of the things I'm involved in at the survey, is studying kind of with our geologic package of units, where are those fractures and where do they occur? Are they preferentially occurring in certain places versus others? So those are the things that we pay close attention to. And those fractures, obviously, they enhance the ability of rock to transmit water. And what we see is that they are most abundant at the very uppermost skin of the bedrock surface, no matter if you have a thick glacial amount of sediment on top of it or not. And we generally see more fractures and conduits in carbonate rock, because carbonate rock, that limestone, can be dissolved pretty readily in a weak, natural, acidic groundwater. So that's where you see the caves, where you hear about the caves in southern Minnesota. Those are generally in the carbonate rock units. Okay. Washington County isn't immune from karst and carbonate rock units, right? Karst describes that process of the dissolution of the carbonate rocks. So, and it also is a way to describe the landscape or the terrain that's produced by that dissolution. So one thing you think about, you hear about first when you think of karst, right, is sinkholes. There's a couple instances of sinkholes happening in southern Washington County. This one is near the Montemedi area in the late 1980s, I believe. And then here's another example on near the Woodbury area on top of the you can see that white St. Peter sandstone and some fractures within that where a pond had drained into that, into those features virtually overnight. This is just a cartoon from the original, or from the first Washington County Atlas that is meant to describe this phenomenon where they think that there was a small cave that formed kind of at the contact between the limestone of the Platteville and then the St. Peter below, and that eventually over time collapsed, and that's what you see today. Okay. So let's get into the maps a little bit more and talk about the data and some of the things we've learned from this last update of the Washington County Atlas. The database plate, as I said, was plate 1. It just includes a lot of data. A lot of different things go into the making of these maps, whether that's a bedrock exposure, a core sample, a water well construction record, a scientific boring record, drill cuttings, which are just when water well drillers put in a new water well, they can collect the cuttings or the little bits of rock they're grinding up, and then they donate that to the survey if we ask them to. And then there's different methods of geophysics we use in some of the mapping too. Here's just a couple of photos from mapping. Sometimes we're out on the river canoeing, sometimes we're in our own soil auger truck. We do often hire out probably 4 to 5 cores that get drilled for each of our county atlases. That comes with a big drill rig and makes some geologic core that we get that looks something like that. We house the samples, we look at them under the microscope, and so on. Zooming in, here's anything that's sort of a small black dot. Here's where we've gone out and mapped where rock is actually exposed at the land surface, what we call an outcrop. And the stars are just areas where we have collected geologic core samples. Another form of bedrock geologic data that I use quite frequently is those cutting sets. So here's just a picture of what those drill cuttings look like from a water well. And then here's an example of what's called a geophysical log. So we have a truck that has a rod on the end of it with some geophysical equipment that measures the very natural gamma radiation coming off of the rock. Shale has higher gamma radiation than a quartz sandstone, just based on the materials itself. Anyway, what it produces is a geophysical log where you can kind of pick out which units you are and know where you are stratigraphically. So that helps the geologist as well. And you can see we've gone and gamma logged quite a few wells across Washington County. So who has a well? A few of us, good. I have a well too. Have you heard of the MWI or what used to be called CWI, the County Well Index? The County Well Index is sponsored by the Minnesota Department of Health. You can go online and find your own well through a record. You can find your own well record through an online search if you're interested. Here's just a picture of where all the wells are in that CWI or MWI in red. And then here's just a separating out where all the wells are that hit bedrock. So the point, and if you were in a different spot in Minnesota, say central Minnesota, north central Minnesota, the majority of the water wells are in the glacial aquifers. In Washington County, the majority of our wells are in bedrock, and really all of the metro area is in bedrock. So here's an example of what a water well record looks like. It's got a lot of construction information, and this is all recorded by the driller. Water well drillers fill these out as they, it's law now since sometime in the 70s, where they have to make a report for each well they put in. And they carefully fill out this geologic material section. So they'll write whether they hit limestone or whether they thought they hit sandstone and so on, and at what depths. And then the geologist takes that material description and then puts on a stratigraphic interpretation based on what units they think are where and so on in the geologic setting. So that's what gets done as part of our mapping. LiDAR is also a very important tool. LiDAR stands for light detection and ranging. It's a remote sensing technology that uses laser light to detect and measure the surface features on Earth. And you can play with LiDAR. There's LiDAR elevation data now for the entire state of Minnesota. It was done by the DNR a few years back. Here's what the LiDAR landscape looks like near Woodbury. And MinTopo is the tool you could Google if you wanted to look at LiDAR, in your yard or, And what a geologist loves about LiDAR is you can calculate out vegetation and remove it. You can calculate out buildings and remove it. So it's like a look at the exact ground surface all over the state. So you can zoom into areas and see that some features look kind of bedrock controlled. These are plateaus of a certain rock unit coming out. And then there's other places where you can just see all of the development that's happened and so on. And then there's other places, if you look at the landscape enough like we do on the screen, you can pick out a glacial landform versus a bedrock landform and so on. So LiDAR is a really good tool that we use quite a bit. Let's talk about the concept of bedrock topography. That's the first thing that gets done in a bedrock geologic map. And that's just, here's a cross section or profiles that were done. Here's the top line and here's the bottom line in black. And so this refers to this line of section and this refers to the southern line of section. And that top line is just the surface elevation of the ground. Okay? And there is vertical enhancement going on here. That's why it looks so steep and so on. And then there's the bedrock elevation. So you can see that they're very different, right? And the bedrock topography is represented by this line. It's the map of the elevation of where the bedrock surface is. And in Washington County, that ranged from the bedrock surface was highest at about 1,050 feet above sea level and lowest at about 350 feet above sea level. Lowest mainly along in the blue here along the Mississippi Channel and some up in the St. Croix. And highest in these dark red features here. Okay, and then you kind of see the change between the two as well. Northern Washington County has a lot thicker glacial deposits above the bedrock than in the southern part of Washington County. And that landscape, that dissected landscape you see is all the ancient river valleys that once existed on the land surface before the glaciers covered them all up. Okay? And along with that, just a different calculation that gets done is if you just take the land surface and subtract the bedrock topography, you get that thickness in between. And this is a map of that thickness of the quaternary material. So you can see it's thicker off in these regions and within narrow bedrock valleys, that's where the glacial materials are thickest, and then thinnest, say in southern Washington County on that bright yellow. Okay? So these are areas where bedrock is closest to the surface. Much of this area is where it is within 50 feet or less of the surface, and that's an important number for land use planning and so on, and just geologic hazards as well. The karst features are generally associated with rock that is within 50 feet or less of the land surface. So, I just find these bedrock valleys pretty interesting. You can kind of get a sense of where the big ones are in the metro area, and these are all buried. You'd never know they'd exist, right? There's a pretty There's a pretty big one right along here, and at the surface, do you know what is here? That's where the Minneapolis chain of lakes exists. So there's things on the landscape and the surface that we know all about that are geologically influenced and based on why they're there. This shows you where it's hard to see the colors, I know, but the blue is where the current rivers are today, and then the black is showing you where some of the really large valleys existed in the past. And here's just our latest compilation. This figure was from the 1989 Hennepin County Atlas, and based on all the more detailed mapping, here's kind of what we envision it today. So it's a very dissected landscape beneath the glacial deposits. And it's a landscape that looks a lot like if you've spent time in Houston County or Winona area. So it looks like that here, but we're just covered by plenty of glacial deposits. Okay. So here's what the bedrock map looks like for the county of Washington. Our highest unit is the Decorah Shale. That's our youngest unit, just occurs in these little areas here in the green, and it goes all the way down through the section into the Mount Simon Sandstone. You get that near the surface along the St. Croix Valley here. And bedrock geology maps just depict, if you removed all the quaternary material, which rock types would be where. That's what it's showing you. What the surface of the earth would look like without the glacial materials there. Okay. So we'll go through some of those different rock types in the stratigraphy if you're not familiar with it. The Decorah Shale isn't actually seen in outcrop in Washington County. Probably the closest place you can get to it is over by Lilydale, if you've ever been fossil collecting in that area. The Decorah Shale is very fossiliferous. So it's a unit well known for that in the metro area. It's a shale. It has that higher gamma signature. Below the shale is the Platteville limestone. And the Platteville is about 30 feet thick or so, and the Glenwood Formation is a very thin shale beneath the Platteville. It's only about 3 to 5 feet thick or so. We just map that together with the Platteville. The Platteville and Glenwood occur in the county in these light blue zones. The St. Peter sandstone is represented by this light cream color through here. So it exists beneath the Platteville. And it's just, your nice medium grain, bright white quartz sandstone. There's right along off of 94 there, right, there's a sand facility where they're using the sand for production. I think that's the only sand operation in the county. The Prairie du Chien group covers the majority of the bedrock surface. That's that blue that you see all across through here. The Prairie du Chien group has two formations within it. The lower is what we refer to as the Oneota Dolomite, and the upper is the Shakopee Formation. The two together are, 200 to 300 feet thick in the county. So it's a thick carbonate unit. It's used quite a bit for quarrying and aggregate for the county, and really for a lot of the state too. The Jordan sandstone is a little bit lower in the section. It's in the yellow beneath the Prairie du Chien. It's what you'd see off in the Stillwater area in there. Again, just a nice quartz, a nice coarse quartz sandstone. The St. Lawrence exists below the Jordan, just in this light blue. It's pretty thin. It's only 30 to 40 feet thick or so, and it's a shale and fine sandstone. The next unit below that is what we refer to as the Tunnel City group. It used to be called the Franconia Formation. We've since renamed it to update our nomenclature with surrounding states. It's what you'd see at the boom site. It's a mix of sort of this black and white or green and white sandstone, and then in certain beds it's much more cleaner or just pure white sandstone. And then the last unit you see in outcrop in Washington County, the lowest one is the Wanawak sandstone. The Eau Claire and the Mount Simon are buried at depth within the river channels, and you just don't see them at the land surface. So the Wanawak sandstone, you'd see, say, along the river, just north of Stillwater, if you've done boating or paddling up through there. It's another one of our sandstone units, coarse to medium quartz sandstone. So another way we depict the geology is through cross sections, and cross sections are just, say, a slice through the map. Here's a cross section A to A prime, and that would just be if we took a slice through the map through here, and it just shows you what the layers look like into the subsurface, or our interpretation of them. So it shows you how they stack in vertical sequence. It shows you if there's any structure, folds, faults, and so on. And here you can see the difference. Where there is a black thick line, that's where the geologist has interpreted a break or a fault line where the rocks have come apart and moved vertically from one another. So you can see that we didn't talk about these thick black lines yet. In southern Washington County, those are faults. Where you can see one particular unit, the Jordan sandstone is this yellow, has been, it exists at one elevation, and then all of a sudden it has a very sharp change in elevation. And so the only way to do that is through breaking the rock and moving it up and down.
You hit my wonderful area of geohazards. Based on the geomorphology of these areas, are these post-Cretaceous faults, or are these still specific geohazards now to any degree?
Great question. We'll talk about the origin and the ages of these faults in a little bit as we go along here, so I don't want to totally blow the surprise. We have reason to believe that they were active during the Paleozoic when the rocks were being deposited. We don't have reason to believe that they are still active today, but they're a scar in the Earth's surface, so that there was some geologic stresses going on that may be the place where they would break again.
And one last follow-up. Are there any road cuts or obvious places one can look to see the fault activity in Washington County?
If you see any, let me know. I'm always looking for those as well. I will show you one photograph. I was on the river along pool right above, well, in pool 2, where you can see a pretty good example. But you have to, you're away, you're on the water, you're pretty far back from the rock, and there's a big train track in between you and there, so you can't get right up close to it, but I'll show you as close as I've gotten. I've worked throughout southern Minnesota too, and there's more examples. If you've ever been to Red Wing, there's one along 61 where you can see the green rock juxtaposed up against the yellow rock. So that's one of the best examples in Minnesota, is in Red Wing there on Barn Bluff. But I'll show you as close as I could get in the Washington County section. Oh, here it is. So this is looking north towards Cottage Grove area or so. The dam would be just right here. And I know it's hard to tell, but this is a zoomed in photograph of this spot right here. So this is tan Jordan sandstone. And that line, if you were to draw the contact, is right here. And then you can see this rock is the Prairie du Chien Oneota dolomite. And it's the same as this rock. So my interpretation is that the Jordan sandstone is up higher in the landscape here. Here's a fault line, it's dropped down, and it's still down, buried through here. So this is that limestone, this is the limestone down low, and here's that same limestone up high. So this is a spot where there's maybe an obvious 75 feet of relief here. And it's about as good as you can get to where I've seen so far. I mean, it is still, I'm mapping Dakota County, so just south of this border here. It's still on my list of things to do to spend some time in the field in this area and get permission to look at this more closely. And maybe find some other areas where we can see the fault too. Because that particular fault is, oh, if I can remember right, I think it's one of these. So there are other places where if it's exposed, we could go and look for more evidence of faulting. And the majority of, there aren't as many outcrops as there are, say, out west in the geologic regions, right? So our majority of the data that I have to work with are water well records. So here's a map showing you the data of all water well records that intersect that Jordan sandstone. And what we do with that data is make what's called a structure contour map. And it's just a map, much like we would of the bedrock surface, but I'm just mapping out the surface of the Jordan sandstone. So here's where it is color-coded. I'm sure it's fairly hard to see, but the Jordan sandstone has over 500 feet of relief just within the county here. It's lowest in elevation, where it's less than 550 feet above sea level, off in southwest Washington County. And you can see that it's quite high in elevation, 900 feet, 950 feet thick or so, between this faulted zone. And then it drops back down here. So this is it's kind of down at the bottom here, but I've just highlighted in red what that is showing in geologic, in a cross section, right? It's low in elevation, and you hit that faulted zone, and it's brought up, and then brought back down. So it's just showing you the displacement of that particular unit. And the displacement is as great as 300 feet or so in along some of these larger faults along the side here, where there is over nearly 300 feet of relief right along that line. And that's important for a number of reasons. Geohazards, but also just, we're mapping these rocks out as sort of containers to figure out where our aquifers are. If a fault is a break in the rock that, all of a sudden you think your aquifer is down here, and then at the same depth, across the fault, you're in a different aquifer. All those things matter for how contaminants might travel through the subsurface and so on. So this is getting at kind of the age of those faults, or what do we know more about these faults? If you look at the thickness of the Jordan sandstone and any of the units below the Jordan, they don't seem to change in thickness at all across these faults. So if you think of how rocks are deposited, just kind of mud into that basin or sand into that basin, the more that basin sinks, the more mud that's going to accumulate above it. The more that basin doesn't sink, maybe even rises up, if a fault is active while these rocks are being deposited, the thinner that rock unit deposit is gonna be deposited. So it doesn't appear that there's any thickness changes in the faulted area in southern Washington County for units in the Jordan and lower. But if you look at the Prairie du Chien, that one 300-foot thick carbonate unit or so, there's some pretty drastic thickness changes near the faulted area. To where it's, in places, 50 feet or less in sort of this middle zone that is uplifted, and then alongside on the spots that are dropped down, it's 250 to 300 feet. So this is, again, if you took that cross section, that same cross section through here is what it's looking like. I know it's hard to see exactly, but these two blue units are much thicker here and here than they are here, on top of what we call a horst, or that uplifted section of the faulted area. Okay, does that make sense? So in order for those thickness changes to be, those thickness changes are so dramatic that they had to occur while those rocks are being deposited 450 million years ago. And I'll show you a couple pictures I have of some outcrops where I have reason to believe that, rocks are deposited, these carbonate limestones are deposited in these nice, you think, quiescent deposits. The layers should be fairly flat. If you look at this one, there's something a little funky going on. The layers are moved around. There's another one here. This is along the river near Gray Cloud Island. I know it's hard to see too, but here's where this layer is just kind of, really demolished, and these layers have been dropped down and then moved up here. And so there's a lot of evidence for the Prairie du Chien to have these disturbed features in the rock layers. Here's another one in a Prairie du Chien quarry in southern Washington County, and you can see that same pattern where there's some layers are much more disturbed than others, and that could be one of our interpretations that we're still looking to spend some more time learning about is maybe that was a time when the fault shifted and there was an earthquake, and that's recording those sediments and ocean floor that was disturbed during that time. So I don't want to spend too much time on this, but getting back into the origin of these features, you may have heard of the Mid-Continent Rift, and that's a Precambrian feature. It's 1.1 billion years old. It exists on the Precambrian geologic map of Minnesota. The Twin Cities, the metro areas were in what's called the St. Croix Horst. So anything that's this pink magenta color is volcanic magnetic rocks. And this is an aeromagnetic map of the state. Anything in the bluer to greens are non-magnetic rocks, kind of granites and things like that. So we see this big cut, and that represents a time, if you want to go to the next one, this explains it a little bit better, where, a billion years ago, not just Minnesota, much of the entire North America tried to split apart. It's a failed rift, obviously, right? We're not on oceanfront property today, but it's where this crust started to get thin, basalt and hot, lava from the Earth's crust came up. It's what, if you've been to Duluth and looked at the volcanic rocks on the North Shore, that's part of this whole sequence. It's the same story here. It failed. Those rocks settled, and they never totally rifted apart, and then more rocks were deposited on top of that, and then later, just a little bit later, like in Ordovician time, they were pushed back up. So it's a little bit geologically of a complex story, but the takeaway point is those Paleozoic rocks we see in southern Washington County, and it's the same thing for western Hennepin County, exist right over the top of those rift structures. So in Ordovician time, there was some movement, could have been far field stresses from what was going on in eastern North America, we're not really sure, caused the rocks to compress together again, and it seems to have broke right along some of those older scars. I think we covered most of that one. So that's the story. I hope that was fun. I guess I always just want to end these with thank you for listening. Thank you for stopping and slowing down for us on the side of the road. Thank you for allowing us access to your property. We have to contact landowners to ask them to drill on their property. We have to contact landowners to ask them to see some of their outcrops. And everybody's always been pretty friendly. So thank you.
You talking about radon?
Can I talk about radon? What about radon?
Yes.
Are there certain areas that have more than others?
Well, that's not my expertise. I'll start with that right away. The Department of Health deals mostly with radon gas. Radon gas can be, we're always looking for geologic reasons why, might be more radon in one area versus another. I haven't done, work on that myself. But it could be that there is more radon over certain certain glacial units than others, and so on. But I really can't speak to that in Washington County. I'm sorry.
You know, you're talking about layer upon layer of different surfaces and building up and so on. If you think the Earth is a marble that's so large, well, after a number of years, like a billion years, is the Earth marble a larger marble, or is there any way of knowing what
Well, I think you kind of can think of it as being fairly balanced out through plate tectonics, right? There are certain parts on the planet that are growing. I mean, a lot of that sediment, the reason why we have that thick sediment layer is that there existed a basin when that was being deposited. And as you're continually accumulating sediments in a basin, that actually creates its own weight, and it's going to subside a little bit there. Then there's other reasons why maybe there's, some compression going on or a mountain building event, and then that's going to raise the crust back up. But if you think about the entire planet and where the plate layers are, sometimes they're diverging and moving apart, like in the center of the oceans, and then there's other times where they're subducting down. So it's it seems to stay the same, right? We've got our own recycling going on in the subduction zones and their own new formations going on in other places based on the plates.
I'll try another one. You're talking about different rock layers and so on, in different places. It varies from place to place in the world. Is there some point as you go into the core that you're going to get the same, is there a core that is all the same material, whatever that is?
There's no place on Earth that has rocks that have been deposited throughout Earth's history. I showed you that slide that talked about, if you look at the entire geologic record, Washington County has a big blank spot between when the glaciers happened 2 million years ago and 450 million years ago. Rock was being deposited in other places of the planet during that time, but not here today. Or maybe it was, and the glaciers have come over and destroyed it all. So there isn't that one place. I mean, geology relies on a lot of correlation, and dating things through different methods or through fossil dating and biostratigraphy, and you can correlate what's going on in the Paleozoics in Washington County with things that were being deposited at that time in China. So it just is it's a pretty mixed bag, and there's really no place on Earth that has the entire Earth's history all in one nice vertical section. Yep.
How do you date? How do you guys date everything?
Oh, I'm getting these hard questions. Well, dating can be done on a lot of different ways. There's there's entire classes and disciplines related to geochronology. In the Paleozoic and the rocks I work on, mostly we have biostratigraphy. So there are certain index fossils or certain types of fossils that occur in those marine sediments that a paleontologist many different paleontologists have spent decades working out and seeing how one particular fossil, they can identify, oh, that's that particular brachiopod and it only exists in that particular layer. And as you move up, they'll find another one. So it's dating with fossils, that's biostratigraphy. One particular fossil are called conodonts, and those are actually these tiny phosphatic teeth where the organism that house these teeth aren't preserved or don't exist, but these little phosphatic teeth are all throughout the whole section. And they're preserved in the shale layers more than the coarse sandstone layers, so it has a lot, with fossils, it has a lot to do with preservation and so on. Another dating method is in the Ordovician, were volcanic events going on off in the east coast, and that volcanic event created an ash cloud, and then that ash cloud was deposited across, and you can date the actual volcanic crystals of an ash bed. Those are great. There should have been more ash beds, then I'd really know more about the geology. So you have to, you have to deal with what you got. But in the Paleozoic, a lot of it's this relative kind of biostratigraphic work.
One last geohazard question. Based on the Cambrian and Precambrian salts and base rock, any activity from the New Madrid, would that transfer over or would it be killed by the base?
Volcanic activity from the what?
Not fault earthquake activity from the New Madrid fault line. Would it just be dispersed as it came through, or would there be a possibility of some slight?
The scar in the crust is there. It's definitely a spot that scientists and geophysicists are paying attention to see if there is any transfer with other events going on.
I was comparing it to the activity in South Idaho, and it gets, as it goes through the state, it just dies. And North Idaho does not feel the activity at all.
Yeah, and I don't think Minnesota's ever felt
Okay.
that specific event either. Val Chandler is our geophysicist at the survey. He can speak more on faults and rocks, or on faults and things like that. And one of the latest ones was in Mankato a couple years ago. And there's some debate over whether that was a real geologic fault, an earthquake that occurred, or had been related to just surface activity and mining and quarrying and so on. So even when you do have a slight shake, it's hard for the geologist to go back and say exactly what caused that too. But yeah.
I got one thing to add, that when you were showing that picture of that fault, there's a ravine next to it.
Mm-hmm.
In a 1895 map, that was called Malcolm Black's Coulee. And
Okay.
that's a coulee that starts when you're at the stop and go lights by County Point. We turn to go to Highway 10. That's where that ravine starts to form and descend. Kind of pinpoints.
Okay.
All right, thank you very much,
Yeah.
Julia. Thank you for